going to be discussing some recent work that we've been doing in my lab that's really been a continuation of projects that I started back in about 2014 as a PhD student. So this really is the product of work from a number of different students I've been able to work with over the past 7 years, both at Colby College, my current institution, and my previous institution, North Carolina State University. And so I'll try and make sure I attribute things appropriately. A lot of this work is driven by trying to understand atoll resiliency, and in particular, what might be primary drivers of atoll island change. And I'm going to use the term motus throughout to refer to atoll islands. One of the big pieces I want to understand is, do we understand what controls them? Is it some kind of internal process like sediment production from coral reefs or algal growth, or is it some kind of external factor like wave climates or large storm events? And to do this, I've worked with a number of students to develop a global atoll database and then look at ways to automate quantification of atoll size and shape and the relationship with the offshore wave climate. So outline of the talk, I'm going to start with a little bit of background of myself and the work I've done, in particular then a bit more about atolls, which I think this audience may be a lot more familiar with than they are up here in snowy Maine in the United States. And then I'll talk about some modeling work I've done looking at potential ways that motus might be forming and the remote sensing work we've been doing more recently to then measure the size and shape of these islands throughout the world. And then hopefully have some initial conclusions. So it's still ongoing work. But a bit of the background, I grew up in Miami, Florida, in the United States. My father is Colombian and my mother is American. I went to college and graduate school all within kind of more snowy locations in the United States, and then was lucky enough to go to the middle of the country, IU Bloomington, for a postdoc to look at the Mississippi Delta, which was ironic, but it was all through using remote sensing. And then I was at North Carolina State and finally up here at Colby College in Maine. And one of the best parts about being up here at Colby College is we have a lot of really good cross-country skiing. So we finally have some snow. It's about -5 degrees Celsius outside right now. And then here's a photo of me actually at the RCEM conference 2 years ago in New Zealand. And so this is on the hike for the Tongariro crossing. So my work actually started looking with flume modeling, physical models in the lab with Heidi Knepp. And I was interested in understanding the role that vegetation can play on sediment transport and thinking of kind of natural proxies like a river or marsh system. A lot of my PhD work was focused on understanding shoreface evolution, in particular kind of sandy islands of more barrier island style. So things like I am apologizing here, apparently it's too late for me. All right. The Outer Banks on North Carolina or some other sandy coasts. And then for my postdoc, I was working on the Mississippi Delta and trying to figure out what might be some of the causes or drivers of the land loss to the internal marshes on the Mississippi Delta. More recently, with graduate students at North Carolina State University, we've looked at the impact of marine hydrokinetic devices, so wave energy converters, on driving potential scour or erosion, as well as looking at scour that might be happening around bridge piers. And a lot of this work has been computational modeling, as well as being able to do a little bit of field work every now and then. A lot of my research is focused on the coast. And one of the important things I always keep in mind for that is if we look at this graph of sea level rise globally over the last 20,000 years from our last glacial maximum, we've had a large change in sea level rise. But over about the last 8,000 years, there's been significant lower rates of sea level rise, less than 1 meter per 1,000 years, in fact. And it's important to realize that any coast that we are investigating today have evolved under these relatively low rates of sea level rise overall. However, when we think about projected rates of sea level rise with climate change, we are predicting significantly faster rates of usually at least 1 meter by the end of the century. And so this significant increase in sea level rise becomes important to try and understand how these systems are going to respond. So when I use the word atoll or atoll, I'm going to use a very, very broad definition initially. And this is going to be that there is some sort of coral reef platform that's encircling a central lagoon. And on this coral reef platform, we may have subaerial land masses that I'm going to be calling motus. And overall, these motus, if they exist, are very low elevation typically. And in the bottom right-hand corner, we can see cross-section of an idealized atoll where we're going from the lagoon on the left-hand side to the ocean. And this light blue is trying to indicate that reef platform that I was talking about. And then the green is showing the motus. So when we think about atolls or atolls, one of the key aspects to recognize is that the formation of the atoll itself is over very long timescales. So over hundreds of thousands to millions of years. And this is actually something that Darwin initially suggested as a formation hypothesis. And here we have an animation kind of showing this idea of an initial volcanic island that over time is subsiding once there is a lack of new volcanism. And as that volcanic island is eroding and sinking from cooling crust, we can have the growth of a barrier island on the outside of it that then keeps pace and creates, in essence, a coral ring. And what we see today as an atoll is actually kind of this expression of the remnant coral reef formation underlain by the volcanic island. And the key aspect is that this is happening on very slow timescales relative to how fast the little islands on that reef platform may be evolving. And we've seen evidence that these motus or cays or reef islets can form and change on the order of decades to centuries, up to maybe 1,000 years or so. So they're quite quick in comparison. So back in 2018, and my undergraduate Sean Daly worked with me to kind of collate a database, a very inclusive database of almost 600 islands that you could possibly potentially think might be atolls. The key part with this database is that we added a lot of qualitative descriptors. We worked off of some existing databases by Goldberg and Stoddart. And we added qualitative descriptors such as, can you count the number of visible motus? Are they inhabited? Is the lagoon infilled or not? Any metrics we could find online about lagoon area or island area, things like that were included in the database as a first pass. And Sean actually checked things by kind of using Google Earth to check every location and make sure that we had the coordinates correct and things like that. And we did this because we wanted to have something to draw from, which we could use with remote sensing. So I grew up in Miami, Florida, which is near the Caribbean, and spent actually a decent amount of time traveling in Latin America, and had gone to a number of tropical islands before my PhD, but I'd never been to an atoll. And the thing that I found is that they are so very different than a lot of other locations. And some of the key aspects when we talk about atolls are the fact that we have this coral reef platform. And so here in the upper left corner is an image of that coral reef platform at low tide looking out from a motu towards the ocean. And we can see some key factors. One, all of the waves are basically breaking at the edge of that reef platform where you can see that white line. The reef platform itself is quite shallow. Here is an image where I took my camera and kind of put it in the water of the reef platform. And so this is about maybe a quarter meter of water depth. And for the most part, there's not necessarily a lot of active coral growth here on the reef platform. Most of the coral is actively growing at the edge on the ocean side where the waves are breaking. And then this image in the bottom right-hand corner is just showing a bird's eye view of that reef platform. So I just took my camera and looked kind of straight down at my feet. And when we think of the motus or the islands where people are actually living, one of the things that you can describe them as is a big pile of kind of rubble, carbonate rubble, sitting atop this coral reef platform. And so here's an example in the lower left-hand corner of me on one of the beaches. And you can kind of see that there's some vegetation and there's some relatively large grain size sediment visible, kind of fining down a bit as you get to the water in the lagoon. And this is better shown in the upper right-hand photo, where we have a trench that was dug, and this is in French Polynesia. And we have grain size varying from very fine grained carbonate sand all the way to large cobbles and boulder size of about 1/2 meter in this image. And that's not uncommon, that there can be significant variation in the grain sizes here. One of the key aspects, though, is it tends to be very focused, very carbonate heavy, which is not surprising given the locations. So a lot of the work that I've been trying to do of answering kind of atoll resiliency or atoll survival has been focusing on 3 different aspects. One, using computational modeling, because that's a lot of what I do. 2, using remote sensing to extend that approach and be able to look at more atolls at the same time. And then 3, when I can, be able to go into the field. And the last one's the part that's been done the least, unfortunately. So at its most basic, one of the ways we can think about atolls in some ways are kind of 3 pieces. So up here in our left-hand corner, we have water, which is separated into kind of the dark, deep blue of our ocean, and then the shallower inner lagoon. We then have this carbonate reef platform that we saw some of the photos of, and I'm just showing that in orange. And then on top of that reef platform, we may have these little islands, reef islets, or motus. If we do a cross section from A to A prime, we can see that what we kind of see visually as the atoll in a Google Earth image, or when we fly to these honeymoon locations, is actually a very small part of the entire structure, which is this old kind of Holocene reef platform underlain by that volcanic island. And on top of that, we'll have this typically sand apron in the lagoon, and then where people live are these small islands. And the interesting part for me always is that the amount of area of land is much, much smaller than kind of the total area that the atoll itself occupies. So kind of understanding what's happening to these motus through time is a lot of the work I'm trying to answer. Back in my PhD, I was trying to answer this using a computer model. And one of the things I noticed was qualitatively, a lot of times when we look at atolls, we can see some significant differences in the morphology of the motus on the same atoll. So here in the upper left, we have an image of Rangiroa, which is in French Polynesia and is one of the 2nd largest atoll in the world. And what we find is on this single atoll, we have some interesting features that are repeated. In the upper left-hand corner on the north side, we have this kind of long connected motu with a relatively very, very narrow reef flat. So you can see the ocean is here on the northern side and the dark blue lagoons to the south of it. And then the motus themselves are this green, and the reef flat is that kind of beigey piece right in front of it. On the other hand, if we then go to the southern part of the same atoll, we can see the motus are significantly smaller. So now the length of the motus, this distance is maybe 1/2 kilometer instead of maybe 10 to 20 kilometers on the northern side. They're much more broken up, and the distance of that reef flat in front of the motus to the ocean varies significantly, right? So here we can see relatively narrow reef flats, and then for this motu, it's much wider. And this pattern seems to repeat itself qualitatively for other atolls in French Polynesia and other locations. So this is also an image of Hikueru Atoll. And here on the northern side, we've got this kind of long connected motu with a relatively narrow reef flat in front of it. But on the southern side, we actually don't really see any motus present, and then a couple of small ones here on the western side. And so a lot of my research was, well, why is this happening? Why do we see this? And can we figure out what processes might be driving the formation and evolution of these islands? And what role might things like tropical cyclones be playing? And more importantly, what might be happening to these locations in the future with accelerated rates of sea level rise? So to answer this, I started with using the numerical model XBeach, which is a open source hydrodynamic and morphodynamic model. But I actually only ran it in hydrodynamic mode. So I was purely looking at, given certain specific conditions, what's going to happen to the waves and how is that going to drive changes in our flow, which would then potentially be driving changes in our sediment transport and then long-term evolution. And so this work is really kind of focused on the modeling side. And I'm going to put the cart before the horse and explain a little bit of the initial conceptual model that was developed from this computational model. We ran XBeach in a simple 1D mode, and from our results came up with this idea that there would be kind of a vertical growth of our reef flat to some equilibrium depth that would be driven by the offshore waves. And then we would expect our reef flat to also reach a certain particular width, again, dependent on our offshore waves and sediment. And once it's reached a wide enough width, we actually can have the deposition of sediment on the middle of that reef flat, which would enable growth and formation of a motu. And I think the most interesting part of this is actually this last idea, where once there is a motu in place, our model predicts that the motu would actually continue to prograde and grow towards the ocean up into a certain point, and that there becomes a critical width in front of the motu on the reef flat that would be dependent on our offshore wave climate. So the model setup, as I said before, was kind of 1D mode, and this is a schematic where I've got very deep ocean on the left side here, which is pretty standard. We might be as deep as 1 to 2 kilometers. And then we'll shallow up to our reef flat, which could be anywhere from 3 to maybe half a meter in depth. I can control the offshore wave height and wave period. I can change how deep is my reef flat, how wide it is, and finally, of course, whether or not I have a motu present in the model. And so given this, here's just an initial visualization of kind of one of the model runs. In blue, we're looking at wave heights. So this is being driven with a 2-meter offshore wave height. And then in green, we're seeing the bed shear stress. And the reason I'm particularly interested in the bed shear stress is, of course, that the bed shear stress generated by the waves and currents would be driving any potential sediment transport. And so here we move from the ocean on the left to the reef flat. There's no motu present. And what we see is that the majority of our waves seem to be breaking right at the edge of the reef flat here in that blue line. And then we get this kind of big peak in bed shear stress near that reef flat edge that then decreases over the extent of the reef flat. And so we can then look at how this varies for different reef flat depths. And so what's shown on this graph is here's my reef flat in black. And then here is the mean bed shear stress for different water depths of a reef flat. So for a very shallow reef flat of 1 meter, that's shown in the purple, versus a deeper reef flat of 5 meters. I've also shown the critical shear stress needed to mobilize all carbonate sands, which is this dashed gray lines here, and to mobilize a carbonate sized boulder. And what we can see is that almost all cases of this reef flat depth, we have enough bed shear stress that we would be able to mobilize carbonate sands over the entirety of the reef flat. So that would imply that if any sediment is kind of on this reef flat or produced near it, it would be able to be moved into the back or not stay on the reef flat itself. But as our reef flat deepens, we do see a decrease in our bed shear stress. So the implication here that we derived was that our reef flat would shallow up to a certain depth dependent on the grain size and offshore wave height. So the other thing, of course, I can change is how wide is that reef flat to start with. And so in this case, I'm playing with 3 different reef flats. So our narrowest reef flat is shown in green and our widest is shown in purple. And what we can see again is that as we widen our reef flat, we're going to have decreasing bed shear stress on average across the entirety of the reef flat. And depending on how narrow your reef flat is, you actually could be mobilizing quite large size sediment, as shown here, where we could actually move these boulder sized carbonates. And this would imply that any sediment that's produced maybe by the corals growing on this outer edge would be mobilized into the lagoon rather than staying on the reef flat. So that we might see this kind of increasing build or width of that reef flat through time. What we find is that once we have a wide enough reef flat, we'll actually start to get an initial low point of the bed shear stress in the middle of that reef flat. And that low point, that minima, could be a location where sediment would then be deposited and not mobilized, which could be a mechanism for potential motu formation. We then ran the model with motus in place. And so here I'm showing for the same water depth, which is our shallow reef flat of about 1 meter, in gray what the bed shear stress was without a motu, and now in purple what the bed shear stress is with the motu. And what we find is that when we have a motu suddenly, our bed shear stress is significantly dampened in magnitude. And more interestingly, it also starts to change in sign. So in this case, a positive bed shear stress indicates movement of sediment from ocean to lagoon, so towards the motu itself. A negative bed shear stress would be driving the sediment towards the ocean instead. And so what I've done here in this last graph is for a range of reef flat water depths from 0.1, so very narrow or very shallow, to 5 meters, what's happening to that bed shear stress with the motu in place. And what we find is that when we have a very shallow reef flat with a motu, we're going to have kind of consistently more positive values of bed shear stress, but that as we deepen that, we're going to start to see negative values. And so what we can then do is play with both the width of the reef flat and the depth of the reef flat for different cases of offshore wave height for 2 meters and 4 meters, and then figure out where we're seeing this change from positive or onshore kind of lagoonward directed sediment transport to negative or offshore directed sediment transport. And that's what this graph is trying to indicate. And the key aspect here is that if we have onshore directed sediment transport, this would imply that any sediment that's generated at our outer edge, at our ocean side of our reef flat, would then be moved towards the motu and help the motu actually prograde towards the ocean. But at some point, we would reach this critical reef flat width where instead of having onshore directed sediment transport, we would now have offshore directed sediment transport. So sediment, instead of moving onto the motu and helping it prograde, will actually be eroded from the motu and moved offshore into the ocean. And so that's kind of this simple 1D model that I'd come up with. And the question that I really had was, well, am I seeing this in reality? Or is this just something that, kind of works in the idealized space? So to answer that, I started to look at atoll morphometrics. And the key thing was, are we seeing this behavior globally? Because we can look at, and I'm sorry for flipping back and forth, we can look at qualitative images. So here again is the northern motus of Rangiroa in French Polynesia, and we have a very consistent reef flat width in front of this motu. It's about 120 to 200 meters in width. And we can look at other atolls around French Polynesia and again see similar behavior for some parts of the atoll. But then on other parts of the atoll, we're not seeing that. And so to answer this, we decided to use some remote sensing and in particular Landsat imagery. So if you remember, I talked about that atoll database that we created. And so these X's are all of the islands that we said might possibly be an atoll. And then we used Landsat images from 2016 to 2019 to create cloud-free temporal composites. And that's what all of the blue dots are. On these composites, we then create a series of Python scripts that allow us to automate classification of the image into land, water, and reef flat, and then calculate morphometrics on each of those different pieces of the image. And that's what the pink dots are showing. So we've actually calculated morphometrics on 155 atolls, which is 1,753 motus, and somewhere around 900 reef flats. And the general methodology for this is that we first kind of create these satellite composites that we ensure are cloud-free. We then classify them and identify the objects. So that would be each individual motu, each individual reef flat, etc. We calculate certain morphometrics like the area, perimeter, orientation. And then ultimately what we're interested in is trying to compare these to the offshore wave climate. And this has really been a large part of Faith Johnson's work, who's one of my PhD students, as well as work from a number of undergrads, including Manny Salas and Bentley Meyer. And so one of the things that Faith has developed is a number of ways to automatically measure certain morphometrics of these atolls. So here you can see an image where purple is indicating water, green is indicating reef flat, and yellow is indicating motu. And I'm going to use certain morphometric terms. So when I describe motu width, we are actually calculating on a per pixel basis for every 155 atoll in our system, how wide is that motu. We can then also measure how wide is the reef flat, shown here in the lower left in these pink lines, or we could measure what's the width from the ocean side of the motu towards the oceanside reef flat, which are these red lines, or the converse, the width from the back of the motu to the lagoon side. And one of the ways that we actually are able to categorize this is we track this for every single pixel on our image, and then kind of keep it in a large pandas database. And we can then bin it either by object or by some other metrics like cardinal position on the atoll. So for example, we could bin it by saying, well, all of these pixels are in the northern part, and all of these are in the eastern side, and these are in the southern side and the western side. And depending on what we're interested in, we may change how we classify or kind of our data. So when we're using Landsat imagery, one of the main issues we run into, of course, is clouds. And so here's an image of Bikini Atoll in the Marshall Islands. And this is a relatively cloud-free image. This has probably got about 10% or less of clouds, but it's still, those clouds are going to interfere with our classification. And so what we've done is a technique that a number of other people have used, which is called a temporal composite. And we take every Landsat image of our location over some time period. In this case, it was 4 years. And we remove all of the clouds. And then we average the remaining pixels on a per pixel per band basis to create this cloud-free temporal composite. And this allows us to kind of automate the analysis significantly. And so what we can do is, here's an example of Katui, also in French Polynesia. We can go from our cloud-free composite here on the left to our classified image, where blue is water, red is land flat, reef flat, and yellow is land, to our object delineation shown down here, where all of our motus are going to be outlined in green and our reef flats are outlined in blue. And if we compare this to a Google Earth image of the same location, we can see that even though Landsat only has 30-meter resolution, we're still actually able to capture a number of the features, like this deep channel that's cutting through the reef flat itself. So this deep channel is about 40 to 50 meters in width, and the great part is it is captured by our analysis. So in French Polynesia, we've actually measured morphometrics on about 60 atolls of about 83 or 80. And there's been some interesting trends, especially when we start to bin it by relative position. And these trends seem to match a lot of things I've been describing qualitatively. So first off, we can look at the lengths of the motus. So how long are they? And what we find is that on the north and eastern sides, we're seeing significantly longer motus, 3 to 5 kilometers, in comparison to the south and western side, where they're much shorter. We can also look at how wide is that reef flat in front of these motus. And on average, the width is much smaller. And in particular, the standard deviation of the width is significantly smaller. And then lastly, we find that almost 100% of the reef flat is actually kind of covered by motus, in terms of thinking about the idea that if a wave was coming and approaching this part, it's going to be hitting a motu, versus a wave coming from the southern side is probably not going to hit a motu. And so that's what this percent length covered by motu shows, is that we have almost 100% in the north and eastern sides, and then only about 50% in the southern parts of the atolls in French Polynesia, and about 75% in the west. So given this, we can actually now start to pull out some of the numbers that might be important relative to my modeling work. So what I'm plotting here is on the x-axis motu length, so how long are they? So that's this kind of value, versus the reef flat width in front of the motus. So that's this measurement. And I've colored the dots from north, south, east, and west. And one of the reasons we've done this is I ran a 1D model in XBeach with the motu. The big assumption with that is that primarily the movement of waves in a 1D case would be on and offshore of the motu, and not that it could be routed around the motu. And so that probably is only a good proxy for very long motus. And what we see is that for motus that are larger than about 3 to 5 kilometers, we get a very consistent reef flat width in front of those motus across the entirety of French Polynesia and actually globally. So I'm showing here just French Polynesia, but we've done the same thing for all 1,700 motus that we've looked at, and this pattern holds true. In addition, we have this pattern where our longer motus are very strongly only found on the north and eastern sides of our atolls in French Polynesia, and much less on the south and western sides. And as kind of our initial thing is our small motus, maybe, kind of these smaller sizes, have highly variable widths of the reef flat in front of them, which again is similar to what we were seeing. So they just kind of highlight that. This is the same graph. The only difference is I've now normalized both my X and Y axis. So I've normalized the motu length by the entire reef flat length. So in other words, if I have a smaller sized atoll, this should help account for it. And I've normalized the width of the reef flat in front of the motu by the total reef flat width. And what my argument is here, that for our large motus, even if, relative to the total reef flat length, we get a very consistent trend that about 20% of the total reef flat width is in front of the motu. In other words, the motu itself is covering the remaining 80% of that reef flat width. And that is only going to be true for these much larger motus. And the small motus have much higher variability, as shown kind of here in this image on the southern portion of Rangiroa. And so Bentley Meyer has actually started to look at pulling data from WaveWatch 3, which is a global wave model, at different locations around each of the atolls that we're measuring northmetrics. And so what I've done very quickly is I took these larger motus, so basically roughly the ones circled in green, anything larger than about 5 kilometers, and I plotted the reef flat width in front of those motus versus the offshore wave height. And what we find is there seems to be a trend that increasing offshore wave height is driving an increasing width in front of the motu. And that is what was predicted by the XBeach model. This is still preliminary, and we now have a lot more motus that we are able to throw into this analysis. So Bentley is now looking at a lot more wave data. He hasn't quite gotten there. So I started with kind of showing our French Polynesia analysis, which is this big lump of pink dots down here in the Southern Pacific. But we do have obviously measurements at 155 atolls, not just in Polynesia. And so what we found is that if we segregate our data into atolls that are found within about 5 degrees of the equator, we're going to call those low latitude. And then between 5 and 14 degrees of the equator, both north and south, I call those mid latitude. And finally, everything above 14 degrees latitude, we're going to call high. And it's not the best naming convention, still working on that. But what we find is, again, some particular patterns that start to pop based on the grouping. So one of the things we can look at are a number of these measurements of width. And so here is just a histogram, a distribution of the widths of all 1,753 motus in our database. And we see some particular trends start to come out. For example, the width in front of the motus, that reef flat width, is this purple, has a pretty strong peak with narrow standard deviation compared to, say, how wide the total reef flat width is for all of these different atolls. If we then pull out some of these measurements for, again, thinking about kind of those low latitude, very near the equator versus the mid and high, we start to see some interesting trends that come out. In particular, our motu widths for both the high and mid latitude, these green and orange lines, are much more constrained. In other words, the motus tend to have a pretty consistent width for atolls that are above 5 degrees. But for atolls that are very close to the equator, we have much wider variation in how wide those motus are. And we also see much wider variation in how wide the reef flats are on those atolls at the low latitude, especially compared to our high latitude, which again then translates to this final width of looking at the distance from the motu to the ocean side of the reef flat. And part of what we're seeing here is the fact that our high latitude atolls are dominated by French Polynesia currently, and we're still working on expanding that analysis. All right, I'm gonna start to wrap up. I showed an initial conceptual model for how I thought motus kind of might form and then evolve. And I've actually, based on some of this remote sensing, developed that a bit more. And what I think happens is that once we have motus placed kind of on the reef flat, we have two regimes that develop. In one regime, we have these kind of small motus that might kind of form towards the back of our reef flat as predicted by our model. And we might have a case where we have maybe a high enough offshore wave energy that sediment and waves are moving enough around each individual motu that it's able to get towards the back of our reef flat, and we get to see a widening of our reef flat. And these motus then stay small. They don't necessarily merge and grow. On the other hand, the opposite may happen, where instead of having these small individual motus, they actually merge and start to prograde to that critical width. And these are maybe the proxy of what my 1D motu modeling was initially showing. And so the question now, of course, is, well, what's driving these two options? Is this the offshore wave climate? And that's the part we're hoping to answer in the next couple of months with looking at our wave watch data. So at this point, this work is definitely still ongoing. And one of the things that we want to do is that now that we've created these series of Python scripts that help to automate a lot of this analysis, we want to track changes to these same morphometrics over the last 30 to 40 years. Now, we've had Landsat available data since the 1980s. Typically for atolls, we're seeing usable data since about 2000s. So we may only be able to look about 20 years worth, but I think it'll still be really interesting to track changes to all of these pieces. And then again, compare this to that offshore wave climate. And hopefully this summer, if COVID, we'll see, I'll be able to actually get some field work again and be going to Belize, to Glover's Reef Atoll, which is one of the ones in the Caribbean, so it's much closer to me, to again look at some instrumentation of measuring some of the wave and sediment dynamics. So there's a lot of references, but again, all of this work would not be possible without the many different students I've had working with me. And this was started as part of my PhD project with Andrew Ashton at Woods Hole in the United States. So I'd also like to thank him. And thank you very much for listening. I'm happy to take any questions.